And now let's have the examples part of our discussion on the elastic properties of materials. Consider the following problem. Sample problem number 1. A weight is suspended from a steel wire of length 1 meter and cross-section area 1 millimeter. The ultimate strength of steel is 400 times 10 to the 6th power Newton per meter squared. What is the maximum mass that the weight can have without breaking the wire? What is the resulting elongation of the wire? The Young's modulus of steel is given to be 200 times 10 to the 6th power Newton per meter squared. So, initial length, L naught is 1 meter. Cross-section area A is 1 millimeter squared. Convert to meter squared. The ultimate strength of steel is given 400 times 10 to the 6th power Newton per meter squared. And Young's modulus of steel is given to be 200 times 10 to the 6th power Newton per meter squared. We are asked for two things. What is the maximum mass that the weight can have without breaking the wire, without exceeding the ultimate strength of the wire? And given that the Young's modulus, Y, is 200 times 10 to the 6th power Newton per meter squared, determine the change in length, determine the elongation of the wire just as it is about to break. Stress is force over area upon which the force is applied. This stress will deform the wire, will elongate the wire. This stress is just due to the weight of the suspended mass. Weight, magnitude is just mass times gravity. If the stress is just about to break the wire, stress is just equal to the ultimate strength of the wire. So, F over A is equal to S. Isolating F is equal to AS. And force is just due to the weight of the suspended mass. Weight is mg. So, about that. This is weight just about to weight of the object that will almost break the wire. So the wire is just about to break. The stress is already at the ultimate strength of the wire. F is equal to maximum mass that the weight can have times acceleration due to gravity. So, M max G is equal to AS. M max is just AS over G. We know A, we know S, and we know G to be 9.8 meters per second squared. We are able to calculate the maximum mass that the weight can have. M max is equal to 40.816 kilograms. Determining the resultant of length of the wire, we use, this is length deformation, so we use Young's modulus. Young's modulus is equal to stress over strain is equal to F over A divided by delta L over L naught. Since the stress is just about to break the wire, stress F over A is just equal to the ultimate strength of the wire. So F over A is equal to S. Delta L over L naught. L naught, denominator of a denominator, will go up to the numerator. So Y is equal to SL naught over delta L. Isolating delta L, elongation, or change of length of the wire, delta L is equal to SL naught over Y. We know S, we know L naught, we know Y. We will be able to determine the change in length of the wire. Plotting in the values, we get delta L is equal to 2.000 meters. Next up, we have sample problem number 2. A bust is suspended from a spring with a force constant or spring constant of 15 Newton per meter. So you have a bust suspended from a spring. Because of the weight of the bust, the spring will be stretched. As a result, the spring will react by applying spring force, F spring. Ultimately, the bust is just suspended, so it is static. You have static equilibrium. Static equilibrium, the net force is equal to 0. Net force is summation of the forces acting on the object. So you have weight of the object plus the spring force applied by the spring on the object. So plus F spring. We know the force constant of the spring, 15 Newton per meter, and the spring is stretched 5 centimeters. Y is equal to 5 centimeters. Is equal to 0.05 meters. Determine the mass of the bust. So, F net is equal to 0 is equal to weight plus F spring. Analyzing this, we use component method. Looking at the X component, looking at the figure, all the forces are vertical, so no X component. We go to the Y component. Y component of F net is F net Y. Y component of 0 is 0. Y component of weight is vertical, vertically downward, so negative W. F spring is vertically upward, so plus F spring. W is just mg, so negative weight is negative mg, plus F spring, force applied by the spring's magnitude is just equal to ky. Minus mg plus ky is equal to 0, therefore mg is equal to ky. Isolating m is equal to ky over g. We know k, y, and we know g to be 9.8 meters per second squared. We are thus able to calculate the mass of the bust. M is equal to 0.077 kilograms. Lastly, we have the following problem. A spring of force constant, 10 Newton per meter, is compressed 5 centimeters using a 1 kilogram wooden block. The spring is released, sending the wooden block sliding along a level or horizontal floor. Assuming that the kinetic friction between the floor and the wooden block is 0.1 Newton, action of friction is to slow down the object. So eventually, the object will come to a stop. How long will the wooden block slide along the floor before coming to a stop? So, we are being asked how long will the wooden block slide. So, we're being asked for time of travel of the wooden block. We can divide the motion of the system into two parts. First, the spring is compressed using the wooden block, and then the spring is released. The spring will push the wooden block, giving it an initial speed. Spring action. Once the wooden block has an initial speed, the wooden block will slide along the floor. You have sliding motion of the wooden block. So we divide our analysis into two parts, spring action and sliding motion. From the problem, we know that the spring constant, K, is equal to 10 Newton per meter. The spring was compressed 5 centimeters or 0.05 meters. The mass of the wooden block is 1 kilogram. And the kinetic friction between the wooden block and the floor when the wooden block is sliding, the kinetic friction magnitude is 0.1 Newton. So first, the spring action. The spring is compressed and then released. The spring will push the wooden block, giving it an initial velocity. Looking at the spring action in terms of conservation of energy, there is no difference in height between initial and final state as far as the spring action is concerned. So, gravitational potential energy will not come into play. So, GPE is equal to 0. No external work done. No external force is acting on the system. We only have the spring. So, work done by an external force is equal to 0. That leaves us with kinetic energy initial plus elastic potential energy initial is equal to kinetic energy final plus elastic potential energy final. Initially, as far as the spring is concerned, we compress the spring, initial speed 0, then we release the spring, final speed V, kinetic energy initial is 0, final kinetic energy is 1/2 mv squared. We compress the spring initially. It is compressed by 5 centimeters. So we have initial potential energy 1/2 kx squared. Final case, the spring goes back to its original position. It pushes the wooden block away. The wooden block, sa final case, will no longer be in contact with the spring. So no more elastic potential energy. Conservation of energy equation tells us 1/2 kx squared is equal to 1/2 mv squared. We know k, we know x, we know m. The only unknown is final velocity or final speed. Isolate v and you'll be able to calculate v to be 0.15813.883 meters per second. Next, we have the sliding motion. After the spring pushes the wooden block, giving it an initial velocity, the wooden block will slide along the floor. the final velocity or speed in the spring action will be the initial speed or velocity of the block in the sliding motion. So V naught is equal to 0.158113883 meters per second. The wooden block will eventually come to a stop because of kinetic friction. So V final velocity is equal to 0. To be able to calculate the time of travel, knowing initial velocity, knowing final velocity, we need the acceleration of the object before we can calculate the time of travel. So to get the acceleration, first we do force analysis. As the wooden block is sliding along the floor, so the motion is in this direction. The wooden block has mass, so it has weight. Because of the weight, the wooden block will press into the floor. The floor will produce normal force N. Kinetic friction will oppose the motion, so you have kinetic friction in this direction. The motion is to the right, it is slowing down, therefore acceleration is in the opposite direction. You have A heading to the left. F net is equal to MA, you have acceleration, accelerating system. F net is equal to summation of the forces. So weight plus normal force plus friction. Using component method, we have the x component and the y component. X component, F net x is equal to x component of A is horizontal, so all of it is in the x component, heading in the negative direction, so negative MA. Weight and normal force are vertical, no x component. Friction is horizontal, all of it is in the x component, negative direction. So negative MA is equal to negative FK, A is equal to FK over M. Okay? So we have an equation for acceleration. We are able to calculate the acceleration to be Fk is 0.1 Newton, M is 1 kilogram. We are able to calculate A to be 0.1 meters per second squared. Magnitude, we're talking about deceleration. If we go back to our figure, the acceleration is negative, is heading in the negative direction. So, converting the magnitude A back to its vector form, vector A is equal to negative 0.1 meters per second squared. Knowing acceleration, constant, accelerating system with constant acceleration, that's non-zero acceleration. So that's what? Uniformly accelerated motion. In uniformly accelerated motion, you have 4 equations that you can use. One of those equations is V plus V naught is equal to V naught plus AT. We know V, we know V naught, we know A. The only unknown is time. So isolate time, and you'll be able to calculate the time of travel to be 1.581 seconds. And that's it for our discussion of the examples part. That's it for our discussion on the topic of elastic properties of materials. Thank you for watching.